The last lecture described how Big Bang cosmology explains the origins of our universe. In fact, the origins of everything that we know of. So, we've got ourselves a universe. That's the good news. Without a universe, we're going nowhere. The bad news is that the universe is still not terribly interesting. It's got a bit of structure. For example, there's a difference between matter and energy. There are atoms, and I suppose you could say that in a sense atoms are complex things. But there's not much structure here. I mean, after all, what's in it? We have lots and lots of hydrogen. Very simple atom, one proton at the center, one electron whizzing around in a shell outside. We've also got lots of helium. The thing about helium is that helium is an inert gas. It's, by many standards, very, very boring. There's not much you can do with helium. So we've got hydrogen atoms, we've got helium atoms, we've got lots of energy, we've got all that cosmic background radiation sort of pumping through. And what else do we have? We've got so much cold, empty vacuum. That's our universe. So here's the problem. How can you move from something this simple to the vastly more varied and beautiful world that we inhabit today? How can you generate complex things with such simple components? How do you build a complex universe containing objects like stars and galaxies and you and me? Remember our definition of complexity. We saw that complex things have structure. They organize components into a given structure. They have a certain amount of stability. They last for a certain amount of time. They have emergent properties. New qualities appear once you create them. And they depend on energy flows. So how can we get more complex things in this very simple universe? What I want to do in this lecture is to take us across the second major threshold of this course by describing how in this simple early universe the first significant complex things were created. It tells the story of how the universe, by a sort of bootstrapping, generated greater complexity from extremely simple ingredients. The first complex objects in this universe were stars. So we're really talking about stars. So how do you make a star? What's the recipe for a star? This is another nice cocktail party question. Everyone has stared at stars. Everyone has probably asked this question. But only in the last century or so has a good scientific answer emerged, and what I'm going to try and do is describe that answer as simply as possible and also describe some of the evidence on which it was based. Okay, let's go back to the early universe. The early universe we saw was a simple place, with vast clouds of hydrogen and helium atoms, energy pouring through them. So the question was, how do you create complexity with these very simple ingredients? You have just two types of atoms, one of which is extremely unreactive. You also have four types of energy. You have the four fundamental forces. Let me just summarize them. Gravity, the force that Newton identified that pulls everything together. Secondly, the strong nuclear force. That holds the nuclei of atoms together. And we're not going to talk about it much in this course. Thirdly, electromagnetism. Electromagnetism is going to loom larger because it's crucial in chemical processes, which we'll look at later on. And the fourth is the weak nuclear force. That's responsible for radioactive breakdown, among other things, but it's something that's not going to loom large in this course. So, with these elements and these forms of energy, how do you create complex things? It turns out that it can be done, which is fortunate for us, because otherwise we wouldn't be here. But how? At this point, we're going to focus on one of our forces, gravity. In a sense, gravity is going to turn out to be the real hero of this group of lectures. Gravity is a force. It's a form of energy. So what it can do is it can do work. It can rearrange things in interesting ways. And we'll see that gravity began the process of taking this simple universe and sculpting more and more complex things. We'll see that gravity also did something else. It also created energy gradients. It created differences between areas of high energy and low energy. And we've seen before, these energy gradients are crucial if work is to be done and complex things are going to be created. Now, what is gravity and how does it work? Newton, you'll remember, described gravity as a universal force of attraction acting between all forms of matter. It operated throughout the universe, in the divine realm as well as in the earthly realm. Every form of matter exerts a gentle tug on every other form. In the early 20th century, Einstein showed that gravity also acted on energy. And there's a very good reason for this. And the reason is, as Einstein also showed, energy and matter are different forms of the same underlying stuff. And one of the odd things about modern science is that it has no widely recognized name for that stuff. But when we talked about the Big Bang, at the very earliest second, the Big Bang consisted of that stuff. There was no difference between energy and matter. So both energy and matter exert a gravitational pull. Einstein showed something else. He showed that the cause of gravity is the geometry of space-time. And Newton was always worried about the idea of gravity as a force because it seemed somewhat arbitrary. In fact, some of his rivals accused him of introducing a sort of something magical into his science because he had no idea how to explain it. Einstein came up with a very elegant explanation which suggested that space-time itself is shaped in different ways. And it's that shaping that affects how things move through it. So gravity is a function of space-time. But I'm not a physicist. Einstein's account of gravity is quite technical and quite complex, and Newton's will take us a long way. So I'm going to stick with the idea of gravity as a force of attraction. It's easier to grasp, and frankly, it can explain all the phenomena we need to understand in this course. Newton showed that the strength of gravity depends on two things. It increases with the mass of the objects involved. It decreases as the distance between them increases. Now, think what this means for the early universe. Imagine a very early universe in which you have these clouds of matter, hydrogen and helium atoms, and imagine that they're distributed perfectly evenly throughout the entire universe. Each atom and each bit of energy is exerting a tiny pull on everything else. But if everything's distributed perfectly equally, what's the result going to be? It's going to be a sort of traffic jam, gridlock, in which nothing can move, nothing can happen. Everything is tugging on everything else with exactly the same force. Gravity can't do anything in such a situation. But imagine now that there are some tiny unevennesses in this universe. Say there's an area where there are a few more hydrogen and helium atoms. The density is slightly greater. Now there, the gravitational pull is going to be slightly greater. Gravity is going to have slightly greater power. It can take that denser region and start smushing it in on itself as all the atoms start pulling in on each other. The result of this is that what gravity can do is take tiny, tiny unevennesses in the density of the early universe, or even in its temperature, and these often amount to the same thing, and it can magnify them. And it can rearrange matter and energy in more interesting ways. What it does essentially is it makes the universe lumpier. By doing that, it creates the sort of differentials we mentioned in the lecture on complexity. You start getting areas where there's a lot of stuff and areas where there's not much stuff. So it's absolutely crucial for Big Bang cosmology that the early universe not be perfectly uniform. Now the question is, can we detect this? Can we observe the early universe? Can we find out whether it was or not? And it turned out that there was a method of doing this. In the 90s, astronomers realized that they could study the cosmic background radiation, and by doing so they could tell a lot about the early universe. A satellite, the COBE satellite, the Cosmic Background Explorer, has provided the crucial instrument for detecting tiny, tiny differences in the energy of this cosmic background radiation. The radiation is incredibly uniform. But with delicate instrumentation, you can, in fact, detect tiny differences. So this is what astronomers started doing in the early 1990s. And what they found was that there were indeed tiny differences in temperature. And what these imply, of course, is tiny differences in pressure. They imply exactly the sort of beginnings of lumpiness that you need if gravity is to get to work, to turn the early universe into something more interesting. There's a very famous picture that many of you will have seen that was published in 1992, and it was associated with the work of an astronomer, George Smoot, and his team. And what they did was they constructed a very famous graphic of the early universe. It looked like a cosmic egg, which was nice, and I'm sure not accidental. But what it really did was it showed the results of meticulous studies of tiny differences in the temperature of the cosmic background radiation. You may remember that picture. It showed areas that were slightly redder, slightly hotter, areas that were slightly bluer, slightly colder than the rest. So here are the differences, the differentials that gravity needed to get to work. And now it gets to work. And what happens? So gravity takes these denser areas. Within them, gravity is greater. So they pull together. All the atoms within them start pulling together. So the universe splits into vast clouds of matter, into billions of clouds, each of which is beginning to contract under the power of its own gravity. Let me quote George Smoot on the significance of the tiny variations he found. He wrote, "These small variations are the imprints of tiny ripples in the fabric of space-time, put there by the primeval explosion process. Over billions of years, gravity magnified these ripples into galaxies, clusters of galaxies, and the great voids of space." And Joseph Silk of Berkeley said, with perhaps pardonable exaggeration, "We are viewing the birth of the universe." It was an astonishing graphic. Okay, now let's take ourselves inside one of these contracting clouds. As the cloud contracts under its own gravity, the pressure and temperature at its center rise. Now, this is a very familiar principle. It explains why if you heat up a bicycle tire, if you pump up a bicycle tire, the pressure increases and it heats up. What's happening is you've got more atoms in a small space. They bump into each other more, they bump into each other more frequently, and they bump into each other more violently. And we read that from outside as an increase in temperature. So what's going on is more and more collisions are taking place within these atoms. And eventually, what we get is a phase change. I've talked about phase changes before. A point at which suddenly matter changes its form. It takes on a new form. The violence of these collisions initially just leads to atoms bouncing off each other. Imagine two hydrogen atoms bouncing together. The positive charges of the protons repel each other and the atoms bounce apart. But once the temperature at the center of the cloud reaches 10 million degrees, that's when you get the phase change. At this point, the protons hit each other so violently, or the atoms hit each other so violently, that their nuclei overcome the resistance of electromagnetism and fuse. And two hydrogen atoms have become a helium atom. This is fusion. Hydrogen is fusing into helium at the center of the cloud. Well, that's wonderful. What we've got is more helium. And I said before that helium is really rather boring, so it may look as if the universe is getting less interesting, but in fact something else is going on. As these hydrogen atoms fuse, a tiny amount of matter is transformed into huge amounts of energy. And it does so in accordance with Einstein's formula E equals mc squared. What that formula says is this: the energy released when matter is converted into pure energy is equivalent to the mass of the matter that's changed multiplied by the speed of light squared. That's a colossal amount. That's the c squared part of the equation. And that's why when you convert a tiny bit of matter into energy, you get a huge release of energy. A hydrogen bomb is doing exactly what happens at the center of a star. And that's why hydrogen bombs release such colossal amounts of energy. So, in our cloud of stuff, we now have a sort of furnace at the center. Fusion is going on, hydrogen atoms are fusing, and something new has appeared, an emergent property. This sort of furnace, this huge release of energy at the center of the star. What this does is prevent the star collapsing any further. Remember, gravity is still trying to smush it together, but now it can't because of this furnace at the center. And the balance between the energy from the center and gravity stabilizes the newborn star, and the star lights up. From now on, its stability will depend on a sort of constant negotiation between the heat at its center, which prevents further contraction, and the force of gravity, which causes it to contract. The fusion that happens at the center explains why stars emit energy. Heat and light from the center travel through each star until eventually it's released into nearby space. In our own sun, it may take a photon of energy 1 million years to reach the surface of the sun. Then, of course, it rushes through the solar system, taking just 8 minutes to reach the Earth. So suddenly what's happened is the universe has lit up. We have light. The universe is more interesting. It's full of these hot spots that are pumping energy into cold space. Now, how long can this go on? Well, essentially, fusion can continue until a star has used up its stores of hydrogen. This could take millions of years. Sometimes it takes billions of years. But what happens when it runs out of fuel? That we'll discuss in the next lecture, and that's a different topic. Recent observations show that the first stars lit up about 200 million years after the Big Bang. The earliest direct observations we know of at present go back to about 500 million years after the Big Bang. But there were a lot of stars present then, so they must have started forming earlier. So suddenly the universe has lit up. Billions of stars have appeared. And now gravity starts working on the stars. It herds them together into larger societies of stars, and we call these galaxies. They may contain billions, hundreds of billions of stars, like our own Milky Way. But gravity then works on galaxies. It herds them into larger groups, which are known as clusters, and herds clusters into even larger structures known as superclusters. And these form huge membrane-like structures through the universe, with vast areas of empty space in between. However, beyond that scale, beyond the scale of superclusters, gravity is too weak to overcome the expansion of the universe. And it's at those scales that you can see what Hubble saw, which is the expansion of the universe. You can see whole groups of galaxies moving away from each other. Now, stars represent a new level of complexity. In what sense? They are structured, they have stability, they show emergent properties, and they're sustained by energy flows. They have structure in the sense that they have a furnace at their core, they have a reserve of fuel around it, and a surface from which they emit energy into space. They are stable, they have new emergent properties such as that furnace at the center, and of course they're generating massive energy flows. That, in brief, is the story of how stars are formed in a simple early universe. Now what I want to do is talk about the birth and death of stars. And I want to talk about the evidence that we use to understand stars, how they're born, and how they live. As always, I don't want to rely solely on authority. I want to try and give you some idea of the evidence. Our understanding of star formation, the process I've just described, depends largely on our theoretical understanding of processes such as fusion, which is extremely well understood by nuclear physicists. It's the basis of fusion weapons. It's also the basis of attempts to create sustained fusion reactions as a way of generating energy. That has proved a very tough challenge, but it's something that physicists have been engaged on for 50 years already. Scientists also understand the operations of gravity very well. So these two things, understanding fusion and understanding gravity, help explain the processes I've just described. But observational astronomy also comes into it. Observational astronomy can identify regions of our own galaxy, for example, where we see huge clouds of matter that appear to be collapsing in on themselves and forming new stars. We can describe these, if you like, as sort of star nurseries. It won't be hard to find a star nursery if you look on the internet, incidentally. The Hubble space satellite has taken, as many of you will know, absolutely gorgeous pictures of the universe in recent years. And many of those show these star nurseries. And you can see the new bright young stars often appearing in clusters like eggs in a nest inside them. If you want, you can check out the Horsehead Nebula, which is a very spectacular and beautiful example of such a region. So, to a certain degree, we can actually observe this process of star formation. It's going on in the Milky Way all the time, and we know where it's happening. Now, what about studying the life cycle of stars? We've talked about their birth. What about their life cycle? This is a tricky proposition, mainly because stars last so long that we can never observe an individual star evolving. This is one of those areas where our limitations, the limitations of our capacity to deal with scales, becomes very important. So we have to find ways around this. And what astronomers have done since the 19th century is to study millions of individual stars and assume that each of them represents different parts of a star's life. It's rather as if you took a sort of mass photograph of millions of humans at one moment in time and then tried to figure out the lifetime of humans by comparing different individuals. Now, how in practice do astronomers do this? Lecture 5 mentioned the invention of the spectroscope by Joseph von Fraunhofer in 1814. You remember the absorption lines. You break up the spectrum from starlight, and you see the different frequencies of light in it, and you find that some of those frequencies are darker than others. There are lines of darkness. These are the absorption lines. And we saw that each of these frequencies represented a particular element which was absorbing light at particular frequencies. So, for example, you can identify lines that show the presence of hydrogen, helium, carbon, and other elements. So spectroscopes can tell us a lot about what's inside stars. They can also tell us about the relative amounts of different chemical elements within a star, because the absorption lines, you can measure the strength of the absorption lines, in fact, how much of the light of a particular kind is absorbed. So we can estimate roughly the proportion of different elements in a different star. And what these studies show is that stars consist, as we've seen already, overwhelmingly of hydrogen and helium. And that's what we expect. We saw the early universe itself consists overwhelmingly of hydrogen and helium. And in fact, the universe today still does. But if you measure them carefully, or if you measure the ratio of hydrogen and helium, you see something else. You see that the amount of helium within particular stars varies quite a lot. In some stars, you find there's a lot of helium, and in fact, more than hydrogen. And this shows us that here we're dealing with a star that's been burning hydrogen for a long time, fusing it into helium, so that what's happening is at the center of the star, a lot of helium is accumulating. In fact, we know this is true of our own sun. Originally, it probably contained about 27% of helium. Now, 62% of our sun consists of helium. And that's the sort of indication that our sun is perhaps about halfway through its stock of fuel, and therefore about halfway through its life. But it's been burning for 4.5 billion years, so we've probably still got another 4.5 billion years before we need to start panicking. We can also measure the apparent brightness of a star, that is to say, the brightness it seems to have from Earth. And we've seen already that if we know its distance, we can measure its real brightness. Now, that's the reverse of the process we saw with Cepheids. With Cepheids, you knew the real brightness, and you could measure their distance. But if we know their distance and their apparent brightness, we can also measure their brightness. That's the amount of energy it emits. Now, larger stars, think back to our collapsing cloud of matter, larger stars generate greater pressures at their center, higher temperatures, and more brightness. So what this means is that by and large, the brightest stars tend to be the largest stars. So if we can estimate the real brightness of a star, we can estimate its mass. So here are quite a few things we can tell about stars. We can tell about their chemical composition, We can tell about their brightness. We can tell, as we've seen, something about their distance, something about their movements. And there's one more thing we can tell. We can estimate the temperature at the surface of a star. And we can do that quite simply from its colour. Basically, if a star is very blue, it's very, very hot indeed. Rigel in the constellation Orion is such a star. Very hot blue star. If it's red, it's probably cooler. Betelgeuse in Orion is such a star. Okay, so astronomers from the 19th century and into the 20th century have built up a massive database of observations about stars, like a vast family portrait. And the question is, how can you use this portrait to figure out how individual stars live and die? Well, this is the first of several examples we'll see in this course of scientists suddenly finding a new way of arranging familiar data so that it reveals new regularities. In 1910, a Danish astronomer, Einar Hertzsprung, and an American astronomer, Henry Russell, distilled all this information into an extremely simple graph that helped astronomers identify the key factors in a star's life cycle. This is what they did. They took two features of each star, of a large number of stars, and they plotted them on a scatter graph. The first feature was the star's brightness. Now we've seen effectively that's a measure of its mass, the total amount of light and brightness that it's emitting, of energy that it's emitting. The second thing is its surface temperature, which can be different than its total brightness. And what they found is a simple correlation. For most stars, the more massive they were, in other words, the brighter they were, the higher their surface temperature. If you look at an example of the Hertzsprung-Russell diagram, you'll see that normally brightness is charted on the vertical axis and surface temperature on the horizontal axis. So what this means is that you end up with a ribbon of stars, which is known as the main sequence, which moves from the top left down to the bottom right of the graph. And most stars appear on the so-called main sequence. At the top left, you have very big, very bright stars, stars that also have high surface temperature. At the bottom right, you have smaller, less stars with less surface temperature. That's the main sequence, this diagonal band. But they also found a number of stars that didn't fit into this correlation. These were stars, it turns out, at the end of their life cycle. They're beginning to behave slightly differently from other stars. Stars on the main sequence are all burning hydrogen and fusing it into helium according to the principles I described earlier in this lecture. They're doing the normal thing that normal stars do during most of their life cycle. The other stars that are off the main sequence are slightly different, and we'll discuss them in their life cycle in the next lecture. They're probably coming to the end of their life. What the graph shows is that the key determinant of a star's life is the size of the initial cloud from which it's formed. In fact, the size of the star itself. This determines its overall brightness. Normally it determines its surface temperature, and it determines the speed at which fusion takes place, and therefore the time it will take to run through its fuel and eventually die. So this one parameter, how big the initial cloud was, is the key to understanding the evolution of stars. Let me end this lecture by summarizing why stars play such an important role in big history. First of all, they count as the first complex things created by our universe. By merely existing, they make the universe more interesting, more complicated, and they generate flows of energy. They represent the first new form of complexity since the creation of the universe. Secondly, stars create the preconditions for new forms of complexity. They provide a platform for building other forms of complexity, and they do so in two main ways. First, from the furnaces at their center, they pump energy out into the cold, empty spaces between them. And this creates powerful energy flows. And these will provide the energy needed to create even more complex things in the future, including ourselves. Secondly, they also create new chemical elements. And we'll talk about that in the next lecture. With new chemical elements, we'll see it was possible to create a universe that, at least in some corners, was much more complex. So this lecture has described how gravity sculpted stars from the simple raw materials of the early universe. What happens next? How do you create even more complex entities? That was the task of stars, and we'll describe how they did it in the next lecture. Thank you. So, describe some of the evidence on which it was based. Okay, let's go back to the early universe. The early universe we saw was a simple place, with vast clouds of hydrogen and helium atoms, energy pouring through them. So the question was, how do you create complexity with these very simple ingredients? You have just two types of atoms, one of which is extremely unreactive. You also have four types of energy. You have the four fundamental forces. Let me just summarize them. Gravity, the force that Newton identified that pulls everything together. Secondly, the strong nuclear force. That holds the nuclei of atoms together. And we're not going to talk about it much in this course. Thirdly, electromagnetism. Electromagnetism is going to loom larger because it's crucial in chemical processes, which we'll look at later on. And the fourth is the weak nuclear force. That's responsible for radioactive breakdown, among other things, but it's something that's not going to loom large in this course. So, with these elements and these forms of energy, how do you create complex things? It turns out that it can be done, which is fortunate for us because otherwise we wouldn't be here. But how? At this point, we're going to focus on one of our forces, gravity. In a sense, gravity is going to turn out to be the real hero of this group of lectures. Gravity is a force. It's a form of energy. So what it can do is it can do work. It can rearrange things in interesting ways. And we'll see that gravity began the process of taking this simple universe and sculpting more and more complex things. We'll see that gravity also did something else. It also created energy gradients. It created differences between areas of high energy and low energy. And we've seen before, these energy gradients are crucial if work is to be done and complex things are going to be created. Now, what is gravity and how does it work? Newton, you'll remember, described gravity as a universal force of attraction acting between all forms of matter. It operated throughout the universe, in the divine realm as well as in the earthly realm. The last lecture described how Big Bang cosmology explains the origins of our universe. In fact, the origins of everything that we know of. So, we've got ourselves a universe. That's the good news. Without a universe, we're going nowhere. The bad news is that the universe is still not terribly interesting. It's got a bit of structure. For example, there's a difference between matter and energy. There are atoms, and I suppose you could say that in a sense atoms are complex things. But there's not much structure here. I mean, after all, what's in it? We have lots and lots of hydrogen. Very simple atom, one proton at the center, one electron whizzing around in a shell outside. We've also got lots of helium. The thing about helium is that helium is an inert gas. It's, by many standards, very, very boring. There's not much you can do with helium. So we've got hydrogen atoms, we've got helium atoms, we've got lots of energy, we've got all that cosmic background radiation sort of pumping through. And what else do we have? We've got so much cold, empty vacuum. That's our universe. So here's the problem. How can you move from something this simple to the vastly more varied and beautiful world that we inhabit today? How can you generate complex things with such simple components? How do you build a complex universe containing objects like stars and galaxies and you and me? Remember our definition of complexity. We saw that complex things have structure. They organize components into a given structure. They have a certain amount of stability. They last for a certain amount of time. They have emergent properties. New qualities appear once you create them, and they depend on energy flows. So how can we get more complex things in this very simple universe? What I want to do in this lecture is to take us across the second major threshold of this course by describing how in this simple early universe the first significant complex things were created. It tells the story of how the universe, by a sort of bootstrapping, generated greater complexity from extremely simple ingredients. The first complex objects in this universe were stars. So we're really talking about stars. So how do you make a star? What's the recipe for a star? This is another nice cocktail party question. Everyone has stared at stars. Everyone has probably asked this question. But only in the last century or so has a good scientific answer emerged, and what I'm going to try and do is describe that answer as simply as possible, and also